Welcome to example 17 in our functions and graphs topic. This is the big performance. We've been looking at asymptotes, we've been looking at stationary points. This is where we get to put it all together and try and draw graphs of these rational functions that we had a look at on the Desmos, the graphing calculator, where we're relying on the graph sketching software to draw the graphs, but now we're going to do it ourselves. Okay, so these are the three main ingredients we need. When we're sketching a graph, we need to look at the asymptotes, so we need to investigate them. We need to work out, are there any stationary points? There may not be, but if they are, what are their nature? And then any kind of key intercept points on the x and y axis. And we can label all them on our final graph. So let's go straight on and work out this first one. Example 17, sketch the graph of f of x equals 5 over x minus 3. Okay, now you might know a little bit about the nature of functions by looking at them. That looks a bit like the function kind of f of x equals 1 over x. We're just playing around with some numbers around it, but we know that the 1 over x is a reciprocal function. We started off looking at that back in right at the beginning of this topic, where we've just got asymptotes on the x and y axes and stuff. I've got a hunch it's going to look like that. It's good to have a hunch, but then we need to actually prove that or demonstrate that. So let's have a look at the asymptotes first of all. Okay, so I'm going to, as I go along, I'm going to label things. Part 1, I'm going to look at asymptotes. I'm going to, okay. So, first of all, vertical asymptotes. And we know that vertical asymptotes exist when the denominator is equal to 0. In other words, any values for x for which we can't actually get a y coordinate. And that's when the denominator of this fraction is 0. In other words, when x equals 3. What does that mean? It means that the equation of the vertical asymptote is x equals 3. In other words, we've got to specify that it's not just x equals 3 is now not just an x value, it's now the equation of the line. But that means straight away that we can introduce a dotted line. I'm going to put them down at the side. This is my vertical asymptote, and I'm going to call that x equals 3. And I want to investigate the nature of it on either side of that. What is it going? Is it approaching at the left-hand side? Does it go down to negative or up to positive infinity, and so on? So we can check the nature of it. How do we do that? Well, this one, it's a wee bit footery for these ones, because the order of the denominator is bigger than the order of the numerator. Okay, so we know that we're going to get some kind of odd things happening later on with our sort of non-vertical asymptote. But let's check and see if there's a function here. We'll factorize it. We don't need to factorize either the numerator or our denominator, but we do want to check as x is or approaches, as x becomes, let's use the arrow instead of equal sign, as x approaches just to the left of 3, okay, just a wee bit less than 3 negative, something like say 2.9. Well, what would happen to the y coordinate? Is it positive or negative? Well, the phi, the numerator is always positive, and just under 3, like 2.9 minus 3 is going to give me a negative value. So that tells me that the overall result, positive divided by negative, is going to give me a negative value. In other words, it's going to tend towards negative infinity. And that means to the left, when x is just less than 3, the curve is going to head down towards negative infinity. What about when x is just above 3? Well, the numerator is always positive because it's 5, it's a constant term. But on the denominator, 3 plus just over 3 minus 3 is going to be positive, which means that overall the y coordinate is going to be positive, and it's going to tend towards that means tends toward negative infinity or positive infinity, just on the right hand side. Okay. So that's going to be the nature of our vertical asymptote, and we'll bag that. Okay. What about the non-vertical asymptote? Well, we know that because of the nature of it, the order here is effectively order 0 on the top, an order of 1, that there's going to be a horizontal asymptote. So we can write down horizontal asymptote. Well, if we're going to do it from scratch, basically what we do is we divide everything by the value of the highest power of x in the denominator. So we divide everything by x. It gives you 5 over x over 1 minus 3 over x. And the point being that we can then consider what happens as x tends towards positive infinity or indeed negative infinity. As x gets very large, what happens to y? Well, as x gets very large, 5 over x on the numerator will tend towards 0, because we know that 5 over a million or a billion or a trillion is a tiny, tiny number, which it might as well be 0 for our calculation's sake. And then we've got a 1 here, and 3 over x is going to be also tend towards 0. So we end up with the y value tending towards 0 divided by 1, which is 0, which means that the equation of our horizontal asymptote is y equals 0. So we can write that down. Horizontal asymptote equation y equals 0. So we've got a second line, and this time it's a here we go. This time it's a horizontal line, and the equation of that is y equals 0. It happens to be the x-axis. Okay. What's the nature of it though? What's happening as x is very negative, and what's happening when x is very positive, as in tending to negative infinity or positive infinity? So the nature, we have to look again at the original function, and which is, well, let's look at it probably better at our amended function here. 5 over x over 1 minus 3 over x. So we've already kind of looked at it, so we'll re-examine it from a point of view of what happens when it's negative infinity and towards positive infinity. What happens? Well, we know that the top number, 5 over x, as x gets large and negative, then that's going to be just a value just below 0. It's going to be 5 over negative a million. It's still negative, isn't it? So it's a 0 negative, just under 0. In fact, let's skip the 0 part. Let's just say we're only interested in the sign now, aren't we? So that's negative. And 1 minus 3 over x, what does that become? As x is very large and negative, 3 over then x will be almost 0, which means it doesn't matter if it's positive or negative. It's just adding or subtracting from 1, which is a huge amount in comparison. So it's always going to be positive. So a negative divided by a positive is negative. So it means that the y value is going to be negative, which means it's going to be below the line. In other words, it's going to be just under 0. So it tells us that as x tends to negative infinity, it's going to be below the line. So my nature is going to be there. And I can also say that as x tends to positive infinity, well, the top number, 5 over x, is going to be just above 0. So it's going to be plus 1 minus 3 over x. Again, although 3 over x is tending to 0, whereas this time it's going to subtract from 1, but it's still positive. And therefore the overall value of y is going to be a positive value, which means that the y coordinate is going to be above the asymptote as it tends to positive infinity. So it's going to be like that. So we've got a general shape. We've got two asymptotes and we've got the nature of those. So we need to just have a look at part 2, which is stationary points. And we can write down stationary points exist when the derivative f dash 0 is equal to x. Well, what did we have as our function? The function was 5 over x minus 3, which we're going to differentiate that, so I'll rewrite it as 5 times x minus 3 to the power negative 1. So the first derivative, just using my differentiation techniques, I've got negative 5 times x minus 3, take 1 away from the power, multiply by the derivative inside here, which is just going to be 1, so there's no change there. In other words, we've got negative 5 over x minus 3 squared. That's my first derivative. So we can say that the stationary points are going to occur when negative 5 over x minus 3 squared is equal to 0. Now we have a wee problem with that, because if we multiply through by the denominator, then that's going to give us negative 5 equals 0, which kind of doesn't really work. The reality is that there is no solutions there. There is no value of x for which the first derivative would be 0. Therefore we can say there's no solutions. So in this case, there's no stationary points, which is kind of odd if you've been used to dealing with quadratic and cubic and quartic functions when there's always stationary points. There are some cases in rational functions where there aren't any stationary points, so that's fine. And the last thing we want to investigate are any intercept points. Now, if you remember, I've got a little wee kind of mantra, a little rule I always use, and you can write it down straight away. You can say that y-intercept when x equals 0 and x-intercept when y equals 0. Okay, and it's not only does it communicate what you're doing, but it reminds you what to do. The y-intercept will be when x equals 0, so that reminds us, well, all we need to do, if our original function f of x equals 5 over x minus 3, all we need to do is to substitute 0 in, and that gives us 0 minus 3 is negative 3, and that 5 over, so in other words, was just negative 5/3 or 1 2/3. Okay, in other words, the y-intercept is at 0, negative 5/3. Okay, and so there may not be either a y or an x-intercept or both, so you might sometimes get one or the other. It just depends on the nature of the curve. X-intercept when y equals 0, they're usually a wee bit harder to find. We sometimes might have to solve a polynomial equation, so we'll see what happens here. So our function is going to be this time 5 over x minus 3 equals 0, because effectively f of x or y is equal to 0. So again, what we were doing there, just like we found with the stationary points, there's no solution. Okay, we can't solve that to get a value for x, so we can say no solution. What does that mean? So there's no x-intercept. It happens, okay? And we know there's no x-intercept because we've just nominated the x-intercept as the asymptote. Okay, so the whole, by definition, there's not going to be a point on the x-axis. Right, so now we've got a time, we've gone through this whole performance, beautiful. So we've started off with our asymptotes, and then we've found no stationary points, and we've found one intercept. So we've actually only got a limited amount of information to put on, but we'll still do it. So graph sketching, we need a graph that's going to take us through the whole diagram. So we've got nice and big. X and Y origin. So we find out first of all that there's a vertical asymptote that X equals positive 3. So I'll put my dotted line here at X equals 3. And I'll write in all the information. So I always write in equations and stuff like that. X equals 3. And so if that's 3 there, we also know that there's an intercept on the Y equals 0. Right now it's going to be hard to see because I'm just going to draw it just underneath the line here, just so you can still see the asymptote. And we'll write it in as Y equals 0, just so that we can recognize the fact that there's a line there as well. We're told that the nature that we found of our asymptote, remember, was, let's have a look, was it knit back up? To the left, it's heading towards negative infinity, and to the right, towards positive infinity. So the nature was it's going to look like that. Okay, so make sure it does. And it's really important, the sketching of it is just, I can't emphasize enough how important it's going to be to do this properly. Okay, you shouldn't do it so that it wobbles around like that. Okay, otherwise it will make it look as though you don't know what you're doing. It's got to be as exact as possible. So you've got to make sure that it does go off and away like that. See, I would, it's kind of difficult with this tablet, but I don't want it to be going away so soon. I want it to kind of almost be parallel, but not quite with the. Yeah, I'll try it from the other way. It's a bit better. Okay, that's more like it. I'm happy with that. We know that the nature of the horizontal asymptote is that it's below there and above here. Right. So these are my points here, and I basically need to join the dots. There's no stationary points, so it's just going to curve down like that, and it's going to head. Now, yeah, if my graph was bigger than that, then it would start to flatten out a little bit. So the idea is I've got an asymptote like that. Maybe I think I'll just do that a wee bit differently, just to make the point. And I'll maybe extend. Oops. Get rid of that. Oh. Just extending everything so that it's good not to just say, well, I've drawn it, therefore I can't actually do any better than what I've just done. Okay, it's always good. You can change or amend things. So there's my right hand part of the curve. I know that the left hand part of the curve is going to be kind of similar. It's going to go somewhere. There's the asymptote there. Oop, and see it's gone towards it, and I don't want to do that. I want to make sure that it doesn't go any closer, that it should always head away from. There we go. That's going to join up there. Okay. I've got, if I had a pencil, I would just tidy it up a little bit. There we go. The one thing that we can mark on our graph is the y-intercept, which we marked in as negative 5/3. It doesn't matter if it's not absolutely to scale, but just make sure that you put the all the key points in. So that's us done our graph. The only thing that's remaining is to actually label it. So please do. Somewhere you should write in the name of the function y equals 5/x minus 3. Okay, and there's our graph. It's taken us quite a while. And please don't rush and draw a scrappy graph. You saw how it took me a number of times to get things the way I wanted. Please don't use ink to draw sketch a graph. Use a pencil and get a rubber and make it the best that you can actually draw. Okay, so I've got one more in example 18, and hopefully that will help get your graph sketching skills up and running. Okay, hope that's been helpful.